Hello, let's get started with section 2.2, definition of limits. And we're actually going to start with some foundational material. And that material is just going to be a review of functions. So what is a function? A function, f, is a rule that assigns each element x in the domain to exactly one element, f of x, in the range. So you can think of f or a function as being a black box. We hand it something, our input, magic happens, and out we get f of x. So x goes in, f of x comes out, x is our input, f of x is our output. So I used the terms domain and range, so let's just give a quick review about what those mean. The domain is the collection of all the values that we can put into our function. And the domain is a collection of independent variables. So let's consider y equals mx plus b. We're really familiar with this. It's the equation of a line. We can make any line we want. I can put in any x value I want. And if I've got a line and it goes on forever in either direction, then any x value is going to give me a y value. Here, x is our input, and we can put anything we like into it. And then we have our output, which is the range. The range is the value of is the collection of all the values we get out of our function. And the range is full of dependent variables. So again, y equals mx plus b. X is the independent variable. Y is the dependent variable. I put something in, x, and I get something out, y. So I've drawn a little map, domain, which is the collection of a, b, and c, f, which is the mapping from the domain to the range, and we get out f of a, f of b, f of c. And you'll notice that each one of these, every a is connected to an f of a, b is connected to only f of b, c is connected to only f of c. These are requirements. So let's see what comes next. We've got a little bit of an example. What is the domain and range of the function f of x equals x squared? If you answer this instantly, congrats. If not, okay. Not only am I going to give you the answer, I'm going to ask you to pause this video and give yourself a little bit of time to think about it. So go ahead, pause, come back when you have an answer. So what's the formal answer? F is defined for all values of x, right? I can put in any value I want from negative infinity to positive infinity, and I'm going to get an answer out. Therefore, the domain of our function is the set of all real numbers, which is written open parenthesis, negative infinity, comma, infinity, close parenthesis. Now, because x squared is always going to be greater than or equal to 0 for all x, the range of our function is open bracket 0, comma, infinity, close parenthesis. This is to say that we can put in any number we like, right? There's no number that we put in that we won't get an answer for, but we will only ever get a positive number out. I can put in negative 10, I can put in positive 10. No matter what, I'm still going to get a positive number out. So now that we remember what a function is, let's talk about taking the limit of a function. And finding the limit of a function is different than evaluating the function fundamentally. And you'll see when we get to our example exactly what this means. So suppose f of x, our function, is defined for all values of x near some point a, right? I pick an a on my x number line, and either to the left or the right of a, I've got values and my function exists there. If f of x is arbitrarily close to L, for all x close to a, we write the following, and we say that the limit of f as x approaches a is L. So what does this look like from an example perspective? Because these were a lot of words, and they don't really mean anything until I show you some new things. So let's do a little bit of screen sharing, and we can work on this example together. So here, I want you to use the graph that I've given you of f to determine the following values if it's possible. It might not be possible, and that's okay. We'll get there. So first, I want you to find f evaluated at 1, and then I want you to find I want you to find the limit as x approaches 1 of f of x. So first, let's see. Oh, This is so hard. F evaluated at 1 exists, and it's right there. And we can say that that's about 1.5. So I'll write down that f of 1, or f evaluated at 1, is equal to 1.5. Now the limit is something different entirely. We're going to get in a neighborhood of 1. So either looking at the values next to 1 on the left or next to 1 on the right, I'm going to march on up. Luckily, my function is defined there. Sorry, that's not what I wanted to do. And as we go from nearly 2 towards 1, our values are decreasing. And as we go from 0 towards 1, our values are increasing. And both of these approach the same value, that 1.5. So we can say that the limit of f of x as x approaches 1 is equal to 1.5. And you'll notice that f evaluated at 1 is 1.5, and the limit of f of x as x approaches 1 is 1.5. And this is not always the case, but we'll cross that bridge when we get to it. So let's go back to our PowerPoint, because we have this idea of a limit, but I want to break it down and talk about left-hand and right-hand limits. So we can take a one-sided limit, right? Our right-hand limit. So suppose f is defined for all x near a with x values greater than our a value. If f of x is arbitrarily close to L for all x sufficiently close to a with x greater than a, then we write the following, and we say that the limit of f of x as x approaches a from the right equals L. So what does this look like? Let's look at an example. So here I'm interested in f evaluated at 2 and the limit as x approaches 2 from the right of f of x. So first, let's see. Let's go to 2 and we jog up. And first we encounter our line with an open hole in it. And that means that our function is not defined there. But if we continue up, we get to a black dot, which I'll color in blue, at 5. So I can say f of 2 equals 5. And here comes the important part. The limit as x approaches 2 from the right. So I'm interested in x values which are greater than 2, which are going to be here. And when we jog up, as we go from 3 towards 2, our values decrease towards the value 3. This means that the limit as x approaches 2 from the right of f of x equals 2. And exactly like I mentioned last time, these two values don't match, right? So f of 2 equals 5 is not equal to the limit as x approaches 2 from the right of f of x, which is equal to 2. 2 does not equal 5. And we can see here that while we follow this graph from the right-hand side, we assume we're going to keep following those lines, but we have points of discontinuity, which is unusual. But this is how a right-hand limit works. So if there's a right-hand limit, there better be a left-hand limit. And indeed there is. And just like before, we've got a big clunky definition. So suppose f is defined for all x near a value a with x values less than a. If f of x is arbitrarily close to some value L for all x sufficiently close to a with x values less than a, then we write the following and we say that the limit of f of x as x approaches a from the left equals L. So again, let's do one more example just to make sure you really feel this in your bones. So my a value in this time I'm interested in, f evaluated at 3, which is pretty simple. We go to 3 and we look and we see, well, there's an open hole. And when we look around the entirety of the rest of the graph, there's nothing here, right? So in that case, we're going to write that f of 3 does not exist. And for shorthand, you are always welcome to write DNE. Any mathematician will know what you're talking about. But even if our function doesn't have a value, we can still evaluate the limit as we approach that function. So this time we're approaching from the left. That means we're approaching from values less than 3. So as we jog over from the left, oh goodness, from the left to the value 3, we can follow our map up, up, up until we approach that discontinuity, until we approach that hole in the graph. And as we're approaching, our values are getting closer and closer and closer to the value 4. So we say that the limit as x approaches 3 from the left of f of x is equal to the value 4. Now, there's a new theorem coming up which is really important. And what does this theorem say? This is theorem 2.1 from your textbook. So assume f is defined for all values of x near a. That means values to the right and values to the left. Then the limit as x approaches a equals L if and only if the limit from the left equals the limit from the right. And this is a pretty important thing. And we'll see what this looks like in just a moment. So here in example 2, instead of using a graph, we're going to use a table. Let me make this bigger so this is the only thing we see. So let our function be the square root of x minus 1 over x minus 1. And for section A, let's fill in the table. So when I plug in, oh, yes, we're just going to fill in this table. So when I plug in 0.9, my f of x is 0.53. When I plug in 0.99, my f of x is just 0.50. When I plug in 0.999, my f of x is 0.500. Now let's do the rest of the table. So let's start at 1.01. My output is 0.498. 1.001, my output is 0.499. And when I plug in 1.0001, my output is 0.499 repeating. Now, you're probably going to ask me about significant figures. And in mathematics, significant figures really don't matter. And I say this as someone who was trained classically as an engineer. If I give you 0.9, I expect something that looks like 0.9, right? So if I give you 0.9 and you hand me something with 10 digits after the decimal, I'm not going to believe what you're saying. But if you give me 1 or 2 digits after the decimal, I'll appreciate that. If I give you something with 3 digits after the decimal, I expect something with 3 digits after the decimal. So that's really the back and forth. So we filled in our table, and you can go ahead and check these values by plugging them into your non-graphing scientific calculator, or you can just trust that these are the values. And our next question is, well, what's a reasonable value for the limit as x approaches 1 of f of x? And here, let's start thinking. I started at a number pretty close to 1, 0.9, and then I got a little bit closer, 0.99, and then I got closer still. So at least the first 3 entries on my table, I'm approaching the value 1. And when I look at the last 3 entries, I'm getting closer and closer to 1, but I'm starting just a little bit past 1. So clearly I'm getting closer and closer to 1. I'm approaching 1. And now let's look at these values in this table. I've got values of something around 0.05 or 0.5, and then I've got values around 0.499 repeating. Well, to me, it clearly shows that as we get closer and closer to 1, our values are getting closer and closer to 0.5. Therefore, a reasonable value for the limit as x approaches 1 of f of x is 0.5. Now, it would be unreasonable for you to say it's 0.51. It would be unreasonable for you to say it's 0.499. And hopefully those make sense. But you'll get the hang of this. You just have to do it a couple times. And next, we're going to talk about example 3. And this is really I apologize. I already had this example worked out from the sum. Anyway, so let's start with example 3, part A. I'm interested in the limit of f of x as x approaches 1 from the right-hand side. So in this case, my blue lines are x. Sorry, my blue lines are my function f of x. And as we approach 1 from the right, our values are decreasing towards -2. In this way, I'm going to say the limit approaches -2. And this is really where we're going to use that theorem. So let's talk about the limit as x approaches 1 from the left. Again, the blue line is our f of x. So as we approach 1, our function approaches +2. And in this way, I'll say the limit as x approaches 1 from the left is equal to 2. Now recall the theorem. The limit as x approaches 1 will only equal a value, will only equal some value L if the limit from the right equals the limit from the left. But we can already see that the limit from the left is not equal to the limit from the right. So in that case, we say that our limit does not exist. And I'm going to use that DNE shorthand. So after completing these videos, you should feel comfortable both finding the limit graphically and finding the limit using a table. So if none of this makes sense, feel free to shoot me an email. If only half of this makes sense, feel free to shoot me an email. If all of this makes sense, go ahead and start on homework 1, which will cover section 2.2. And that is it for me.